Today's video will work with what's called implicit differentiation. First thing, we're going to look at f of x in parentheses squared and see if we can find the derivative. Well, this is a chain rule case because we've got a function inside of another function. We know with the chain rule that we do the derivative of the outermost function, keeping the inside function the same, and then we multiply by the inside function's derivative. So we will bring the 2 out front. This will now become f of x to the first, and we'll multiply by the inside's derivative, which would be f prime of x. So we really have 2f of x times f prime of x. And that's the general idea that we'll use in implicit differentiation. It really just comes from the chain rule. Let's look at now if that was a y. Now, when we take our derivatives, all we have seen so far is our derivative of y with respect to x. So another way this could be written is we could do our derivative of y, which would be 2 times y to the first, but because our derivative is with respect to x, we would have to say times y's derivative, dy dx. Now, we've been more frequently, when we take the derivative of something, not using dy dx and seeing y prime. So another way you could do that is you could have y squared, and that would become 2y times y prime. Okay, all three of these are really the same thing. This one kind of shows you why we do it, because it's really just a chain rule. And the reason we need to multiply by the derivative of y, so like a y prime or a dy dx, is because we're taking the derivative of y with respect to x. Okay, x is the variable we're taking the derivative with respect to. And we'll see that'll come into play today. So we know we can easily take the derivative of something like y equals 2x cubed minus 1. We would get y prime equals 6x squared, and the derivative of the negative 1, that goes away. And even if y is not by itself, we know we can easily add our y over, subtract the 1 to the other side, and that can give us y equals 2x cubed minus 1. Okay, so we know that we can rearrange it. Well, not every function can be rearranged easily. Functions that we can write with y by itself, we call those explicit functions because they can be explicitly written in terms of another variable. So the two examples we have there are y equals square root of x cubed plus 1. Y is written explicitly in terms of x. And we have y equals x times sine x. In general, you have some function y equals f of x. Some functions cannot be defined explicitly with y by itself. For example, x squared plus y squared equals 25, so in other words, a circle. Something else, x cubed plus y cubed equals 6xy. The reason the first one cannot be written explicitly with y by itself is because if we try to get y by itself, we would need to do the plus and minus when we take the radical, which is really giving us two separate functions. The positive one is representing the top half of the circle, whereas the negative radical is representing the bottom half of the circle. So we say that this cannot be written explicitly because if you get y by itself, then you really get two separate functions. Similarly, if we have x cubed plus y cubed equals 6xy, this cannot be easily solved with y by itself. So we need other methods with which to take the derivative. Again, keep in mind, we're going to think of, just for the first example, we'll think of y as being f of x so we can see it as being a chain rule. After that, we will just use y primes just to make the notation a little bit easier. We will be using what's called implicit differentiation. It's differentiation on a function that cannot be explicitly written with y by itself. So let's take that x squared plus y squared equals 25. And what I'm going to do is I'm going to rewrite the y as an f of x. And again, we're just going to do this for this first example or so, you can see where it's coming from with chain rule, and then we'll probably just use y primes after that. So we've really got f of x squared equals 25. So we're going to take the derivative, and we're taking the derivative with respect to x. So derivative of x squared is 2x. In this next part, we have a chain rule, kind of similar to what we saw on the first slide. So we'll have 2 times f of x to the first, but then we have to multiply by the derivative of the inside of those parentheses, which would be an f prime of x. And then our derivative of 25 is just 0. Well, we're trying to find what f prime of x is. So we'll just get that by itself now. We'll subtract the 2x over. That'll leave us with 2f of x times f prime of x equals negative 2x. And then we'll divide everything by 2f of x. We'll now have f prime of x. The 2's divide out to 1, and you're left with negative x over f of x. And keep in mind, f of x is like the same as saying y. So what we're going to do now is we're going to look and see what if we had done the problem leaving it as a y. Well, we would have had x squared plus y squared equals 25. Remember, we're taking the derivative with respect to x. So in general, if you take a derivative of a portion that is using some variable other than x, because that's what we're taking our derivative with respect to, you just have to multiply it by a y prime. Okay, and then that again is coming from the chain rule. So this would be 2x plus 2y times y prime equals 0. So notice it's the same as that row in blue there on the left. We just have y's instead of y primes. And again, where that's coming from is the chain rule and the fact that our derivative is being taken with respect to x. So if you take a derivative of something with some other variable, you got to multiply it by a y prime. So we'll just do the same thing. We'll get the y prime by itself. We'll have 2y times y prime equals negative 2x. We'll divide everything by 2y. So you get y prime equals negative x over y, which, as you notice, is actually the same thing as we have there. Well, part B wants us to find the equation of the tangent line at 3, 4. Remember what y prime is representing. It is a function that can help give us the numerical value of the slope of our tangent line. So we can just sub in the 3 for x and the 4 for y, telling us that the slope of our tangent line will be negative 3/4. So writing our equation of our tangent line, we'll have y minus 4 equals negative 3/4 times x minus 3. So that is our tangent line at the point 3, 4. Now, just to show you, we're actually always doing implicit differentiation. It's just kind of hidden. If I give you the equation y equals 3x squared plus 7x plus 1, let's say, we have always been doing the derivative of y with respect to x. On the left, we've kind of just been automatically putting in a y prime. Really what we're doing is we're saying the derivative of y is 1, and then we have to multiply by a y prime because we took the derivative with respect to x. So really, we've already been doing this the whole time. It's just kind of been hidden. So this then just becomes y prime equals 6x plus 7. So you've really been doing implicit differentiation the whole time. Just the derivative of y would be 1 times the y prime, so we just see it as the y prime. So we are now going to just work with the y primes because we know that where it's coming from. It's coming from chain rule, and the notation's just a little bit easier with that. So in part A here, we're going to go ahead and find what y prime is. Well, we're taking a derivative with derivative of y with respect to x, sorry. So anytime we take a derivative of something with a y, we'll need to multiply by y prime. So derivative of x cubed is 3x squared. We'll have plus 3y squared, but because we are taking a derivative of a y thing, we need to multiply by y prime. And again, that's just coming from a chain rule. Now over on the right, we need to be careful. We have a product rule going on. So let's think of this as 6x times y. So we'll do the regular 6x times the derivative of a y, which would be 1 times y prime, plus the derivative of 6x, which is 6, times the regular y. So what we really have is we have 3x squared plus 3y squared times y prime equals 6x y prime plus 6y. Once you take the initial derivative in implicit differentiation, the remaining steps are almost always the same. Our goal is going to be to get all the y primes on one side. We will factor out a y prime, and then we'll divide over the other stuff so that we have y prime by itself. So it doesn't matter which way you go. Maybe let's bring all the y primes over to the left. So we'll have 3y squared times y prime. That was already over on the left. We'll have to subtract the 6xy prime over to the other side. The 6y was already over on the right, and we'll have to subtract the 3x squared over to the right. So we've gotten all the y primes on one side. We'll now pull out the y prime, leaving us with 3y squared minus 6x. That's going to be equal to 6y minus 3x squared. And our final step is we'll divide everything in our parenthesis over to get the y prime by itself. So we have now found y prime, which was our task in part A. Part B wants us to find the tangent at 3, 3. Well, we first need to use our derivative, our y prime, to find the numerical value of our slope at 3, 3. So our slope, we'll just sub in 3 for all the y's and 3 for all the x's. So in the numerator, we'll have 18. We'll have 3 squared is 9 times negative 3, which will give us negative 27. On the bottom, we'll have 3 squared is 9 times 3 is 27 minus 18. Well, this is just going to give us negative 9 over 9, which is just negative 1. And what that is, that's the numerical value of our slope, which we can now easily write our equation of our tangent line. We'll have y minus our y value equals our slope times x minus our x value. So really the only difference in finding that numerical value of the slope is we had to plug in for the y also. Now our task in part C is to find at what points in the first quadrant is the tangent line horizontal. Well, if the tangent line is horizontal, we know that the slope should be 0. So we are going to take our y prime and we'll set it equal to 0. So we're going to take this here and make y prime 0. Well, first thing to notice is everything has a 3 that could be divided out of it. So we can rewrite this as 3y minus x squared over y squared minus 2x. And actually, that should be 2y, sorry, not 3y. So we now want to find when this will be equal to 0. And we have to be careful. We have to see where it might be undefined. So let's first set that bottom equal to 0. And this is telling us where it would be undefined. So when y is equal to plus and minus square root of 2x, that's when it would be undefined. Because we're working with just the first quadrant, really we only have to worry about the positives. So we know that y cannot equal square root of 2x. So we just want to keep that in mind because that will make it undefined. Well, we now want to know when this fraction is 0. And a fraction is 0 when the numerator is 0. So we'll just worry about when the numerator will equal 0. We'll add the x squared over, and we'll divide by 2. And we have that y is equal to x squared over 2. Now the algebra here is going to be a little bit tricky. Keep in mind throughout this, x is always going to be greater than 0 because we're just looking in the first quadrant. We just want our x's and y's to be positive. So again, the algebra is going to be a little tricky. What we're going to do is we're going to go back to our original problem and we'll sub in for y so that we have something just in terms of x that we can then solve. Okay, we basically created a system of equations. Our original equation was x cubed plus y cubed equals 6xy. So all we'll do is we'll sub in for y the x squared over 2. And again, what we're doing here is we're trying to find the points in the first quadrant where there's a horizontal line. So we'll have x cubed. When we cube each of those, we'll have x to the 6th over 8. And will be equal to 6x cubed over 2. Well, 6x cubed over 2 is really 3x cubed. And if we subtract an x cubed from both sides, we'll get x to the 6th over 8 is really equal to 6x. Or sorry, is going to be equal to 2x cubed. Because it's 3x cubed minus 1x cubed. If we multiply both sides by 8, we get x to the 6th equals 16x cubed. We'll get everything on one side. To get it equal to 0, we can pull an x cubed out, and we're left with x cubed minus 16. And when we set these equal to 0, well, x cubed equals 0, we'll get x equals 0. Remember, we said x had to be positive because we were working in the first quadrant, so we don't care about that. With the other one, when we set it equal to 0, we'll get x cubed equals 16. And when we take the cubed root, we'll have cubed root of 16. Now, just a clever way to write this, which will help us, 16 is really 2 to the 4th. So this is really cubed root of 2 to the 4th. And when you cube root something, the denominator of your exponent's really 3. So this is really 2 to the 4/3. And the only reason we're doing this is you'll see shortly, we're going to have other 2's involved, so it'll make our life a little bit easier. Well, we knew before, so this is our x value. So we know it's going to be 2 to the 4/3, comma something, for our point where we have a horizontal tangent line. We knew from what we subbed in before that y was equal to x squared over 2. So we're now just going to sub in our x value of 2 to the 4/3. We'll square it and put it over 2. Well, 4/3, when you square it, we'll end up getting 8/3. So we'll have 2 to the 8/3 over 2. Well, 2 is really 2 to the 1st, so that's really 2 to the 3/3. 8/3 minus 3/3 will give us that y is really just 2 to the 5/3. So you can see the algebra was a little tricky here. Okay, but what we just did is we found the point in the first quadrant that our equation would have a horizontal tangent line. And if you were to plug this in, you would see it's about 2.51 or so and 3.17 or so for the y. Okay, just so you can get a general sense of where that really is. And here is a visual of that, where that horizontal tangent line would end up being. All right, so we're going to look at a couple implicit differentiation examples just to make sure we have the process down solid. Remember, anytime we're taking a derivative that has a y in it, we need to multiply by y prime. That's coming from the chain rule and the fact that we are taking the derivative of y with respect to x. So in this function here, we'll do 5y to the 4th, but we have to multiply by y prime. Then we've got a product rule going on here. So we'll do plus the regular 3x squared times derivative of y squared, which is 2y times y prime. And then we'll do the derivative of the 3x squared, which would be 6x, times your regular y squared. Now we can just go ahead and straight take the derivative of 5x to the 4th, which will be 20x cubed, and the derivative of 12 will just be 0. Once you have that initial implicit differentiation done, again, our steps are almost always the same. Get all the y primes on one side, stuff without y primes on the other. You'll pull a y prime out and divide it over. So we'll leave the y primes on the left. This will give us 5y to the 4th y prime. We're going to neaten this up because 3 times 2 is 6, so we'll have 6x squared y times y prime. And we'll move the other stuff to the other side, so we'll have negative 6xy squared minus 20x cubed. 2 steps to finish it off. We'll pull out a y prime, leaving us with 5y to the 4th plus 6x squared y. And divide that over to give us minus 6x y squared minus 20x cubed all over what was in our parentheses. Now, if you had chosen to get the y primes to the other side, the only difference you would notice is that every single sign would be changed. So you'd have plus and plus on top, minus and minus in the denominator. That is equivalent, though. So we'll look at another implicit differentiation example. We have sine of x plus y. That's going to be a chain rule case. So our outer function is the sine. Derivative of sine is cos, keeping the inside the same. But then we've got to multiply by the derivative of the inside. Well, derivative of x is just 1. Derivative of y is 1 times y prime. On the right-hand side, we've got a product rule. So we'll do regular y squared times the derivative of cos x, which is negative sine x, plus derivative of y squared, which would be 2y times y prime, times regular cos x. Now, the tricky thing is this cos x is going to have to distribute to each of these. So we're going to have cos x plus y. 1y prime is really just saying y prime. So we are going to have y prime cos x plus y. And neatening up this other side, this will really just becoming negative y squared sine x. And we'll have plus 2y y prime cos x still. Okay, and now it's very similar to the other examples. Get all the y primes on one side, pull the y prime out, divide it over. So maybe we'll get the y primes to the left. So we'll have y prime cos x plus y. This will have to be subtracted over, so we'll have minus 2y y prime cos x. The negative y squared sine x stays put. And this will be have to subtract it over to the right, so minus cos x plus y. So again, if you decided to get the y primes to the right rather than the left, you would just notice that your signs would all be different. 2 steps to finish it out. Pull the y prime out. You'll be left with cos x plus y minus 2y cos x. And divide everything in the parentheses over. To get your final derivative. So we'll look at one last example of implicit differentiation in this video, and for this one we're going to find y double prime. So to start out, we'll take derivative of x to the fourth, which is 4x cubed, plus derivative of y to the fourth. We've got to do a chain rule like we've seen before, and because we're doing a derivative of y with respect to x, it'll be times the y prime. So we'll have 4y cubed times y prime, and then derivative of 16 is 0. So we'll get y prime by itself. This will give us 4y cubed times y prime equals negative 4x cubed. And divide the 4y cubed over. We'll have y prime equals 4 and 4 will divide to 1, so we just have negative x cubed over y cubed. So now we will do the second derivative. We're going to have to do a chain rule. So we'll have that y double prime equals our low, which is y cubed, times d high, which will be negative 3x squared, minus high, which is negative x cubed. D low, we're taking a derivative of y with respect to x, so we'll have 3y squared times y prime, all over low low, which would be y to the sixth. Now, we want to have only x's and y's in our second derivative. So what we would have to do is we'd have to plug in for y prime what we know it's equal to from our first derivative. So we would have y double prime equals, I'm going to neaten this up and write it as negative 3 y cubed x squared. I'm going to switch this to a plus because we've got the minus. So plus x cubed times 3y squared, and then we'll put in for the y prime negative x cubed over y to the third. And then that's all over y to the sixth. So technically this is fine for your second derivative. We have only x's and y's. But what I'm going to do is I'm going to neaten it up and show you something kind of cool that happens to make it even neater. What we can do is when we rearrange it, we'll find that we'll have an x to the fourth plus y to the fourth in there, which was the original problem that we know is just 16. So again, if it asks for just the second derivative, which it does here, you could leave your answer like this. I'm just showing you one last kind of interesting thing, I think. So we'll have y double prime equals negative 3y cubed x squared. That negative is going to come back in. We're going to have 3x to the 6th in the numerator. And then you have y cubed in the denominator, y squared in the numerator, so we'll just have 1y on the bottom. And that's all over y to the 6th. Well, when you divide by y to the 6th, you're technically multiplying by 1 over y to the 6th. If we multiply that first term by 1 over y to the 6th, basically 3 of the y's cancel out, leaving us with negative 3 x squared over y cubed. And then the other one, we'll have a y to the 6th times a y in the denominator, so we'll have minus 3x to the 6th over y to the 7th. We'll get a common denominator now. We'll have to multiply each of these by y to the 4th. So this will be y double prime equals negative 3 x squared y to the 4th minus 3x to the 6th all over y to the 7th. Well, notice they both have a minus 3x squared that can be pulled out, leaving us with y to the 4th plus x to the 4th all over y to the 7th. And this is where kind of the clever thing comes in. We know a y to the 4th plus an x to the 4th from our original thing is really just 16. So you could replace it with 16, which would make it even nice and neater. So this would be negative 3x squared times 16 over y to the 7th. So that would just give us negative 48 x squared over y to the 7th. So again, technically, if it asks for just the second derivative, you could stop at this step right here, because you've replaced any y primes, and you have only x's and y's in your answer. But if you wanted to make it neater, you could keep going, and notice we were able to make this much neater than it was. And this should say a y to the, this should say a y to the 7th here, and not y to the 2nd. That's all for today's video. We'll see you next class period.